Swayam Prabha. Digital India. Educated India.
Hello and welcome to this course on gas turbines and jet engines. Okay. So, today's class is the first class of week 2. So, overall this is lecture 6 of this course, and today we are going to learn gas turbines with reheating. Okay. For an ideal case, this means that we are going to study Brayton cycle with reheating. Okay. We will learn what is the concept of reheating. So, the concepts that will be covered today is Brayton cycle with reheating, and then analysis of Brayton cycle with reheating and performance characteristics of a reheat cycle. Okay. So, before we go into the detail of reheat cycle, if you remember in the previous class I had finished by asking a few questions on regenerative Brayton cycle. Okay. So, I will quickly go through quickly discuss that part again, so that we can know what are the answers to those questions. Okay. So, starting with you can see the performance characteristics of the regenerative cycle drawn in the previous class. We had drawn the efficiency versus R, okay. And we have seen that for regeneration the characteristics are completely different. With increasing R, the efficiency keeps on decreasing. Okay. What is the reason for this? So, we had discussed that we should think about this. So, the reason for this is physically what happens in a regenerative cycle. Okay. So, I have a regenerative cycle here. Physically what happens if I keep on increasing the value of R? Let us say that something like this, there this is 5, this is 6. If I increase the value of R from 2 to let us say that we go to 2 dash, then we would get a cycle like this. The scope for regeneration decreases significantly. If we keep on increasing the value of R, the scope for regeneration keeps on decreasing further and further. As a result, because there can be less regeneration, the efficiency decreases in this case with R. Okay. The second point was that what is the limiting value or maximum value of this efficiency corresponding to R equal to 1, the maximum value occurs, and we can see directly based on our calculation we had obtained that eta equal to 1 minus C by T. So, for R equal to 1, okay. So, for R equal to 1, this means that eta equal to 1 minus 1 by T. So, for example, for T is equal to 5, okay, means realistic value. Inlet condition is 300 Kelvin, maximum temperature is 1500 Kelvin. The value of small t is equal to 5. So, this maximum value of efficiency is 0.8, which is a very high value, but of course, there is no point or there is no cycle which can be run at R equal to 1. So, it is just a theoretical value, but still the values remain high at smaller values of R. Okay. Similarly, we can find for other cases. So, like that for t equal to 2, for example, this maximum value is 0.5, t equal to 4, for example, this maximum value is 0.75 and so on. Okay. Now, the final question was that at what condition this efficiency there is a crossover between the efficiency of the regenerative cycle and the standard Brayton cycle. At what value of R, after which the standard Brayton cycle efficiency is higher. Okay. So, for that we can equate the two efficiencies. Let us say that for a particular value of R, the efficiencies are equal. Okay. Let us say that. Okay. So, again the same drawing we have here. So, let us say that for some value of R, the efficiencies are equal. For reheat for regeneration cycle and standard Brayton cycle. Okay. So, which means that 1 minus C by T is equal to 1 minus 1 by C. Okay, very simple relation can be obtained from this, which means that C by T is equal to 1 by C, which means that C is equal to root T. Okay. Previously also we have seen this. So, what happens when C is equal to root T? So, T 2 by T 1, which is also equal to T 3 by T 4, this is equal to root over T 3 by T 1, from where we had obtained previously. If you just take a product of these two, you will get that to be equal to T 3 by T 1. So, from here we had obtained that T 2 is equal to T 4. So, at T 2 equal to T 4, the efficiencies become equal, and that is understandable, right. That is understandable, because what we had seen was that once T 2 becomes equal to T 4, let us have a quick draw again. Okay. That is understandable, because once T 2 is equal to T 4, okay, let us say that we have reached a case where T 2 is equal to T 4. At this point, after this point, if I try to increase R, there is no scope for regeneration. So, this is the limiting condition where regeneration becomes equal to 0, and if I forcefully add a heat exchanger beyond this point, then the heat exchange will be in the opposite direction and the efficiency will actually decrease compared to if there was no regenerator. Okay. So, this with this we finish the regenerative cycle discussion. Couple of things that we should remember as compared to standard Brayton cycle. For regenerative cycle, the efficiency is going to be higher for smaller values of R or for reasonable values of R. So, you want to design a cycle which should have higher value of efficiency, of course. The work output is not different, the work output remains exactly same as that of the standard Brayton cycle. The increase in efficiency is because of lower heat requirement from the fuel in the combustion chamber. Okay. So, now we move forward. We have studied two types of cycles, one is standard Brayton cycle, second is regenerative Brayton cycle or regeneration cycle. Both are representative of different types of gas turbines, standard gas turbine and gas turbine with regeneration, but we are considering ideal conditions. Okay. Now, we will go into a third type of second type of modification or third type of cycle, which is known as reheat Brayton cycle. Okay. So, what is this reheat Brayton cycle or reheat cycle in short? So, we have seen that regeneration can increase the efficiency, okay, but it does not increase the specific work output. So, if we want to, if we need higher power output, okay, from a gas turbine, we will need to increase the mass flow rate significantly. So, we want to know if there is a way to increase the power output without increasing the mass flow rate of air, okay, without increasing the mass flow rate of air. So, which means that for a given mass flow rate, we are increasing the power output, okay, or we want to increase the net specific work output of the cycle. So, the way to do this is to add another heating process after expansion in the turbine. Okay. So, we have seen how we will use the brighter color. So, in this case again we have a compressor. So, inlet occurs at ambient condition, okay, going from 1 to 2, then 2 to 3 is standard heat addition. So, which is the combustion process, okay. We already know that from 2 to 3 we have the combustion process. Now, instead of fully expanding in the turbine or going to, by fully expanding we mean that going to the ambient pressure, decreasing the pressure such that it reaches ambient pressure. Instead of that, we reach an intermediate pressure after expansion in the turbine. This is known as reheat pressure. Okay, this is at state 4. So, this enters the turbine at state 3 and comes out at state 4. Okay. Now, it is passed to a second combustion chamber and again it is combusted and heat addition occurs and the temperature is taken back to a high temperature. Generally, this temperature T5 is kept equal to T3 because that is the maximum temperature that is possible in a cycle, which we call as material limit or depends on the turbine blade material. Okay. So, typically we take T5 equal to T3, although it need not be the case, but this is for practical purpose this can be taken to be T5 equal to T3, okay, this is 0.4 and after that there is a second expansion and we go to state 6, okay. Let us say that some point state 6 and then, so that occurs in a second turbine, okay. You can see that this is the first turbine T1 and this is second turbine T2. And the exhaust gases, in real case the exhaust gases will go out at state 6. In our ideal cycle we are closing out the process by a constant pressure heat removal going from 6 to 1. Okay. So, this is a reheat cycle, TS diagram of a reheat cycle. I leave it up to you to draw the PV diagram, which is also important. You should learn, think on your own and try to draw the PV diagram for the equivalent cycle, for the reheat cycle basically corresponding to this TS diagram. Okay. You can pause here and think and try to draw the PV diagram. We will continue ahead. Okay, we will try to analyze this reheat cycle. So, again when we say analysis, we are saying that we want to find the efficiency and the net specific work output in terms of the design parameters R and the temperature ratio, and in this case another additional parameter is needed such as the reheat pressure, okay, because we do not know what should be the pressure at 0.4. So, how this division should be made between say going from, instead of going directly to this pressure, at what point should we again start heating, okay, that we are not sure. So, to start this, let us take this diagram also. Okay. So, we will take this we will duplicate this slide and continue from there. Okay. Okay. So, we will define a set of variables. So, let us say that the pressure ratio from 3 to 4, okay. this pressure ratio is R A. Okay. This is equal to P 3 by P 4. Similarly, R B is equal to P 5 by P 6. Now, because P 6 is equal to P 1 and P 3 equal to P 2, this also means that overall pressure ratio R, which is equal to P 2 by P 1, should be equal to R A into R B. Okay. And similarly, we define corresponding C values. So, C is equal to R to the power gamma minus 1 by gamma, which should be equal to C A into C B. What are C A and C B? C A again is similar to C, it is defined as R A to the power gamma minus 1 by gamma, and C B is defined as R B to the power gamma minus 1 by gamma. Okay. So, this means that C is equal to C A into C B, and we have already discussed that it is assumed generally that T 5 equal to T 3. So, that we get maximum heat addition. Why will we go to a value which is lower than the limiting temperature which can be achieved or used for that material? Okay. And of course, we cannot go to a higher temperature because that is not possible, or with that the turbine is going to fail. So, now with this we can define the, or we can write the net work output as C P T 5 minus T 6 plus C P T 3 minus T 4. Probably I should have written T 3 minus T 4 first, but does not matter. Okay. Or let us just for the sake of standardness, let us say that this is T 3 minus T 4. It is the same thing, just I am changing the order, plus C P T 5 minus T 6 minus C P T 2 minus T 1. Okay. Net work output. So, then net specific work output, sorry, this is the net specific work output, then the non-dimensional form, remember we non-dimensional by C P T 1 inlet energy. So, C P will get cancelled and we will be left with T 3 by T 1 minus T 4 by T 1 plus T 5 by T 1 minus T 6 by T 1 minus T 2 by T 1 plus 1. Okay. So, we can simplify this further in terms of our known notations. Okay. So, this is equal to, we should go to the next slide probably. This is equal to T 3 by T 1 is equal to what? T 3 by T 1 is equal to temperature ratio T, small t. What about T 4 by T 1? T 4 by T 1 on the side, if we do a calculation, that line has gone. So, T 4 by T 1 is equal to T 4 by T 3 into T 3 by T 1. Okay. Now, T 4 by T 3 we know that this is equal to 1 by C, and this T 3 by T 1. So, T 4 by T 3 is in this case not 1 by C, it will be 1 by C A, okay, 1 by C A, and T 3 by T 1 of course is equal to T. Okay. So, this is T by C A. So, minus T by C A. Then T 5 is equal to T 3. So, T 5 by T 1 also is equal to T, and T 6 by T 1 we can do a similar analysis as similar to T 4 by T 1, and you will see that this is equal to T by C B. Okay. then T2 by T1, this is equal to C minus C and then plus 1. Okay. Let us continue this in the next slide. So, the net non-dimensional net, remember the full term, non-dimensional net specific work output. Why non-dimensional? Because we are non-dimensionalizing using CPT1. Net because we are subtracting the compressor work input, and specific because this is per unit mass flow rate. Okay. So, this is equal to T minus T by C A plus T, like what we have derived in the previous slide, I am rewriting, minus T by C B plus minus C minus C plus 1. Okay. So, this is the net non-dimensional net specific work output. Efficiency also we can find general expression, but we will do it later, there is a reason for that. Before that, we want to find out whether there is a specific value or specific reheat pressure where we get the maximum work output. Okay. Reheat pressure which gives us maximum value of W net by CPT1, okay, which means that maximum specific work output also will occur at this pressure. Okay. In other words, what is this reheat pressure? So, this reheat pressure is the pressure of at 4 and 5. So, P4, P5. So, for the process from 4 to 5, which is the reheating process, this is the reheating process. Okay. So, basically we want to know at what point should we stop the expansion in the first turbine and then start the reheating. Okay. So, this T3 by T4 we have seen that this is equal to C A and T5 by T6 is equal to C B. Okay. So, we want to know how we should divide this C into C A and C B. So, to do that we can take a derivative of this term W net by CPT1, assuming constant temperature ratio and constant overall compression ratio. So, constant T and constant C, we can take a derivative with respect to either C A or C B, because both of them are not independent, C A depends on C B. So, we can take derivative with respect to one of this and then equate it to 0 to get the maximum value, okay, maximum value of or the condition for maximum value of work output. Okay. So, for maximum work output, we take d d C A, we are taking with respect to C A, W net by CPT1 and equating it to 0. Okay. So, if you do that, the first term leads to 0, second term you will get T by C A square, third term again will go to 0 after taking the derivative, fourth term. So, C B can be written as C by C A, okay, which will give us after differentiation with respect to C A, you will get T by C, okay, and fifth and sixth terms vanishes. So, you are left with this, which means that C A square is equal to C or C A is equal to root C. Okay. So, this is the condition for which we get the maximum work output, okay. C A equal to root C, okay, which means that is also equal to C B, because C A into C B is equal to C. Okay. So, each of them are equal to root C. So, when what does this condition imply? It means that T 3 by T 4 is equal to T 5 by T 6 is equal to root over T 2 by T 1, T 5 by T 6 is equal to root over T 2 by T 1. Okay. Or we can write this as, we can keep it in this form. So, if I want to write in terms of pressure ratios, we can write that. Okay, let us try to simplify it further. So, since T 3 is equal to T 5, it also means that, so it also means that T 4 is equal to T 6. Okay. So, the cycle will look like this. So, both the expansion processes will be equal, because T 3 by T 4 equal to T 5 by T 6. So, 1, 2, 3, 4, 5, 6 and 4 and 6 are at the same height, and 3 and 5 are at the same height, and the temperature versus entropy graph. Okay. So, this reheat pressure then can be written as, so because we know that P 3 by P 4 is equal to P 5 by P 6 based on this condition, it means that P 4, because P 5 and P 4 are equal, we can write that P 4 or P 5 is equal to root of P 3 P 6. So, this is the optimum reheat pressure. Okay. So, with this optimum reheat pressure, we can write the we can find what is the maximum work output and efficiency. So, the maximum work output will be equal to W net by CPT 1 in non-dimensional form. Okay. So, remember that now C A is equal to C B equal to root C, okay, for this optimum condition. So, optimum work output so, this is equal to 2 T minus 2 T by root C minus C plus 1. Okay. This is just same as the case which was shown here, but instead of C A and C B we have written root C for both of these. Okay. Then the efficiency corresponding to this is equal to, so W net by CPT 1. Okay. Remember that W net itself is CPT 1 multiplied by this 2 T minus 2 T by root C, okay, minus C plus 1 divided by, so not CPT 1, so sorry, I made a mistake, W net by heat addition. What is the heat addition? There are now two heat addition processes, okay, Q in. So, these are equal to Cp, let us go back to the cycle, T 3 minus T 2 and T 5 minus T 4, okay. T 3 minus T 2 plus Cp T 5 minus T 4. So, now we can take out CPT 1 common from both the numerator and denominator, and after rearranging you will get a final expression of this form. I am directly writing down, please try to derive this on your own, only 2 steps are involved. Okay. 2 t 1 minus 1 by root c minus c minus 1 divided by 2 t minus c minus t by root c. Okay. Again I will remind all of you that this expression is not a formula or not to be used as a formula. This has been derived so that we can find the or plot the performance characteristics. So, efficiency and work output variation with respect to T and C or T and R. Okay. So, finally, we will finish with by drawing the performance characteristics. So, how does the efficiency vary? So, efficiency here, although the work output increases, but we also need more heat addition, right. So, it is seen, we can plot later on by doing actual or using actual numerical values. So, here I will qualitatively compare it with standard Brayton cycle. So, if the efficiency for standard Brayton cycle varies like this, for the reheat cycle the efficiency will vary as will be slightly lower, okay, slightly lower, and is also a function of T. So, after plotting this can be obtained. Okay. With increasing T, so increasing value of T. So, for example, this can be T equal to 3, T equal to 4, T equal to 5. Increasing value of T, it goes towards the standard Brayton cycle efficiency, but still always remains lower than the standard cycle efficiency. Okay. Why the efficiency has been lowered? Because now we are needing additional heat also, and thus although the work increases, the additional heat actually compensates for that and the efficiency comes down. What about the work output? If we draw the work output, we will use this blue color itself. Okay. Net specific work output. So, this actually is significantly higher as compared to standard cycle. Okay. Remember that for standard cycle also this was a function of T. Let us say this is T equal to 3, T equal to 4 and T equal to 5, okay, reheat cycle, blue color is reheat cycle. The corresponding standard cycle values let us show by red color. This may be the corresponding T equal to 3 for standard cycle. T equal to 4. Quantitative comparison I will show later by plotting all the graphs using numerical values, T equal to 5. So, the heat, so work output for any value of T is significantly higher than the standard Brayton cycle values, and this is what we had wanted from this, right, from reheating. We wanted to increase the net work output from the cycle, so that we can use less mass flow rate, okay. But it has come at the cost of lower efficiency. So, in the next class or in subsequent classes we will see how actually we can combine this reheating and regeneration, so that these drawbacks are not there and we get both high efficiency as well as high work output. Okay. So, with this we will conclude today's class. We had learned what is reheating for Brayton cycle, and we have also derived the condition for maximum or optimum reheat such that we get the maximum work output, and we have seen how the performance characteristics compare qualitatively with a standard Brayton cycle. Okay. These are our references, okay. And with this we finish today's class. Thank you.